All right, so this is kind of a different paper than I usually read. It's kind of reinforcement learning-ish. Yeah, so the name of the paper is called RoboCat. That is what stuck out to me, and that is why I decided to read the paper. Also, I kind of saw some of the results online, and it was kind of interesting to see what they did. Here, let me go to the the website that they kind of put out for it. So, um, kind of the goal is to have an agent that can move an arm, and it's kind of a generalist agent. So you want this agent that can move an arm, and then it can adapt to scenarios it hasn't seen before. I mean, that's kind of what our reinforcement learning is. You want a generalized agent, but they do it in a really simple way compared to most reinforcement learning algorithms. And you can kind of see the environment here. It's kind of like this bucket where it does things with this claw. And the goal is to teach it on some tasks and then have it learn other tasks. But they also have like 100 to 1,000 examples. You want to have this agent and you want to be able to fine tune it on those examples, and you want it to do well on those examples. So a small amount of data to fine tune this generalized agent. Um, but they also say they want to have they want to be able to have it generate its own data, which can then be fed back into the agent, and then you can train it again, and it'll be even more generalized because now it has more tasks based off based off the new data it generated. So yeah, but anyways, we'll get into that. The goal is kind of a generalist agent for this environment. Um, yeah, so that's the goal, and the way they do this is first we'll go into the model because normally, how do you really do reinforcement learning? It's let me switch this. You usually have like an agent, and the agent performs some type of action, and then there's a reward that goes with that action, and then the agent is it may have a value function, stuff like that, and the agent wants to try to maximize its reward in the environment, and you kind of you may create like a probabilistic agent that tries to maximize the sampled actions given a certain state that it's in to um, to reach the highest reward, and that's what you usually have. But that's very complicated. It's very hard to if you've ever tried to use say PPO for example, it's very difficult to train. There's a lot of hyperparameters, and it's very difficult. But RoboCat, and I think the reason they call it RoboCat is because they follow the the Gato um, uh, model that was released maybe it was a year ago, maybe less than a year ago, very recently, and that instead of if you can take a guess at what you would do instead of doing this, your first guess may be, I'm going to use a transformer. That's exactly what they do. And if that was your guess, then yes, that's exactly what they do. Good job. You are good job. You know how to solve every machine learning task. Just throw a transformer at it. I mean, essentially, that's kind of what we're leading to. But yeah, they just throw a transformer at it, and they model this as a sequence task, because transformers are easily scalable and it's easy to model things. If you can make it a sequence task, it's easy to model it as a sequence task. So they have they kind of abstract this a little bit, and they say we want a policy pi that gives us an action at time t given O sub t and G sub t, where O sub t has kind of two parts to it. O sub t is composed of x sub t. X sub t is our state, so that may be, they have that right Where do they have that? Yeah, so x sub t is kind of the state, and that's kind of like what's my current velocity of of the robot arm, or what's the current position of the robot arm. Yeah, sorry, right here. The observation and like the velocities and the robot joint positions, because this is a robot arm. You need to know that information to know how to move. And then the second part of O sub t is I sub t, which is kind of the image, the image the robot can see. I think they have that somewhere down here, like an example of what the robot sees. Let's see if I can find it. It's a long paper, but um, there we go. So it's kind of like an example view, or this may be one of the cameras where you have it on the claw itself. So it's on the claw, and that may be the image you feed into the model. So that's O sub t. Where was I? Right here. So yeah, that's the first part, O sub t. And then that's our image. And you can kind of think of this as what is the current state of the robot in. G sub t is the goal state. So this is our goal. So like say our current state may be something like this, where I have like an apple here, and then the goal state may be something like this, where I have the apple here. And the goal state does not change, so the goal state is constant while the state changes. So the apple may move over here because the robot arm maybe like nudged it or something like that, or maybe it picked it up or something like that. So the robot knows where the apple is, but it also knows where it wants to move the apple. So this is kind of where do you want to go, and this is where you currently at, and the goal is to have a model that a model p sub theta or a model pi, a policy pi that can predict that, and they do so autoregressively using an autoregressive transformer model. So what they do, they have it down here, is they take the model. Yeah, they have a tokenized trajectory. So if you know how a transformer works, you have your tokens. Like if this was a sentence, this would be like and you tokenize this would be like maybe hello, my name, and so on. And then you feed this through a transformer, and then it predicts maybe you take this last token, and then that predicts my name, and then it would predict is. So I'm going to assume you know how a transformer works, but and if not, I made a video about transformers. Everyone has made a video about transformers, so go check out transformers. They're amazing. You can basically throw a transformer at everything, and it does well. So highly suggest checking out how transformers work. But anyways, transformer sequence to sequence. So you take a sequence and it outputs a sequence of the same length, and you can take this last token, or maybe that's the next prediction, which you then feed in autoregressively, and then it predicts the next token. In this case, they have a sequence where like the first one is x, or the first token is x sub 0, so that's our like vector state. That's what is like my position, what is my position of the arm, what's my velocity, and that may be represented by one vector or two vectors or something like that. And then your next vectors is maybe multiple vectors is your image vectors. I think they represent this as multiple vectors. They use something called VQGAN to encode it, and the way they encode it is by using they use a lookup for a codebook. So I made a video on residual vector quantization, and vector quantization and a codebook lookup is basically like a way to discretize a continuous something in a continuous space. So like if I have an image that's pretty continuous, but like if I have an image patch, so you would patchify the image, and then you would feed this through a VIT, and then of course you feed it through a transformer, and then this would output a token for each of the image segments that you put in, and then you feed each of those segments into the vector quantization, and that will output one discrete token for each of the image segments. So you would have multiple image segments unless you somehow compress that a little bit, and I think they just keep it as multiple. So you have your X, you have your robot arm state, you have your image state, and then you have your G sub t or G sub 0. And I guess it wouldn't be G sub 0, it'd just be G sub t, and it would also be multiple vectors because that's an image. Let me erase this. So that's an image. That's like the image state you want to get to, and then you feed this through a transformer. And if this is our original state, then you would want this to, so it would output all the tokens, and then you would want it to output the action to take. So in like the apple example, say I'm like right here, the apple's here, like this is my O sub 0. So this is this whole part right here, and this is say G sub 0 or G sub t. It doesn't matter because it doesn't change. Or the apple needs to go here. Then my action may be like the action would it would change your robot arm state, or maybe there's like a way that it knows how to handle an action. There's an action that you give the robot arm, and it knows how to change itself based off that action. And say it's like, okay, I want to move it a little bit. I want to, and I know my arm is like right here. Maybe I want to move my arm in that direction to kind of push it. So it's like move my arm this way, or bottom towards the bottom right at this velocity or something like that. And it would output that in the action vector. And then the action vector would be put back in the sequence. So this is also your G sub t. And then you have a sub 0. So now you have a full sequence of your state and your state action pair. And then you would add, so that's the first part right here. And the second part would just be x sub 1, I sub 1, and so on. This is your second state. And you do this for t states, or in this case, they do 1 to t plus 1, so 1 to, in this case, it would be t states. And you can do the nice thing is if you can tokenize this, let's assume you have this data. We'll get into how they get this data in a sec. Let's assume they have this data where you have this full sequence of some agent that already did this in an environment using that arm, using these actions. So you have some agent that already did this. You have some agent that already has all these actions in it. All these actions, all the states, X, all the image states, and so on, to move the apple from the top left to the bottom right. And you have this whole sequence that you already have in a data set. And you train the transformer autoregressively. They have the loss down here, normal autoregressive loss, or normal log likely loss, I guess cost. Yeah, and you normally, or you do this using a normal transformer loss. And they predict two things. They predict, first off, the action, but they also predict the they also predict the image parts. So instead of just predicting the action, if you have it predict the image tokens, so instead of it just predicting this action here, instead of it just predicting this action here, the next action given the sequence there, given the previous or given the current state, you also have it predict the image of where it wants to get to. And that way, the model inherently has to have some understanding of the environment itself, at least according to the image that it has. because it has to model that. If it didn't have to model the image itself, then it doesn't necessarily have to use the image. And since it's a transformer, we don't necessarily know how or what exactly it's modeling, but it may not model the image part. But if you have it predict the image, if you have it predict the next image state, then it has to directly model that, and it can't implicitly model that. So that's what they do. They 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 have these sequences for multiple different uh, types of arm movement actions, like stacking stuff and moving stuff, and they train a transformer autoregressively on those tasks. So let's go to the training loop. So they have this data set right here, and they have it on a bunch of tasks. They have it on different color shapes. They have it on like cogs or gears, and then they have it on like fruits and vegetables. And then what they do is they train this agent using both a simulated environment and a real world environment. And they do it they do it autoregressively with the transformer. So the model is a transformer. And then what they do is they collect more. So they have this large data set that they already have, and they kind of create a generalized. The idea is you can create a generalized agent using that big data set, and then say like now that you have trained this thing on blocks and on like maybe stacking blocks and moving the fruit into a bowl and placing cogs on this sort of stand thing, then you can say, well, I know that you know how to move these gears. I know and I know you know how to move these blocks, but I want to give you a task that you haven't seen before, but it's in the same environment and it uses the same objects. So they take the generalized agent that's trained autoregressively using the transformer, and they give it 100 to 1,000 examples of a new task they want it to work with. So is what they show here. They fine tune it on that new task, and now you have this specialized agent that can do this new task fairly well that it's never seen before. That wasn't in this large data set, and it only uses 100 to 1,000 examples, which isn't like it's still a lot, but it isn't that much compared to most reinforcement learning agents need a lot more data than that. And the way they collect data is they just, I mean, we'll get to that in a sec, but the way they show here is here they have some humans and they use like a remote control to do it themselves. But we'll get into the data in a sec after this training loop. And then what they do is they feed they have this specialized agent generate data on this task that isn't in the big data set that has 100 to 1,000 examples, and then they generate more examples. So maybe they increase this 100 to 1,000 examples to 10,000 examples, and they just have this robot play around with this task. And then they take that, so they have that here, and it generates its own data, and then you put that in the big data set again. So you put that in this big data set, and now you have more data, and then you retrain a model on that data, you fine tune it on another task, or maybe the same task that you wanted to fine tune it on before, and then it does even better, and you continue this loop, and the goal is to have it create this big data set, and it keeps on, and it can improve itself because it kind of becomes more generalized, and it can work with these tasks more and more, and it has more and more data to work with, and it can improve itself because of that. So that's the goal, and they use this transformer autoregressively to do that. But I mean, the biggest problem the biggest thing that I was thinking of whenever I saw this is how do you get all this data? It's not that easy to get this much data on this specific arm. And the way they get this data is down here. Well, first, what exactly are the actions that they do? So they do RGB objects here, like blocks, and then they do gears. They do fruits in a bowl, and then they do sheep matching. So, and they also do this in different. They do this with different arms, so you can kind of see like this arm is a little bit different from this arm right here, which is a little bit from this arm. And they also have an arm, like these arms have only two parts of the claw, while this one has three, so they have different arms that they're dealing with. They don't just want one arm to do this, they want to generalize it to different arms. Having one arm is only so good. So they have different objects they move, they have different, it's the same like, environment space, but different things to work within the environment. And the way they generate this data is here. They have data produced by an agent already trained, and it's like you have this reinforcement learning agent, and you put it in a simulated environment, and you can have it generate data there. The problem is the simulated world is only so good. The real world sucks because it's so messy compared to the simulated world, which is you can make it a perfect world. There is no entropy in your simulated world, but no matter how well you try to model the real world in your simulation, it's only going to be so good. There's going to be a disconnect between the simulated data and the real data. And then they use human generated data, where the human operates the claw itself and generates a bunch of data using that. And then they have the self-generated data, which we talked about. The good part about the simulated data is it's very smooth. A reinforcement learning agent is probably not going to be very jerky, while a human working with a claw is probably going to be very jerky with its movements. So there's kind of a trade-off between the simulated data and the real-world data that the human works with, but the self-generated data is hopefully going to be really good, assuming that the other two data sets are really good. Now, let's assume that we have we have a good data set to start with, and we are able to fine tune a model. So you're able to collect this data set that is pretty good, which just means that you have these agents that you've trained and you've manually created all this data. That's really good data. So you're able to train this agent that that is kind of generalized. It knows how to do a few tasks, and then you fine tune it on this other task. Go back up here. So you fine tune it on this other task, and then you want it to start generating data for that task. So let's say I have a agent that, let's say I trained an agent that already knows how to, say, move an apple from B to A. Like this is a flat surface, and it knows how to move something from one place to another on a flat surface, and it can do so really well. But what we don't have is, say we have an elevated surface right here. So this is kind of an elevated surface, and we want the robot to kind of move it, to move an object A to C over here, where C is some elevated place. So we have a ton of data. Let's say we have a ton of data where we just move an object on a flat surface, but we don't. And that is in our training set. But our fine-tune set is where we want it to move something to an elevated surface. So we only have 100 to 1,000 examples doing that. So we fine-tune our agent to do this, and we want it to start generating data for that. Now, there's two kind of tricky parts to this, and they mention that here. The success classification, how do you know that the object is on the elevated surface? And how do you know when to reset the task? Say the robot arm moved it over here, and then it dropped it right here. How do you know that it dropped it right there and that's a failure? Or how do you know when you failed, and how do you know when you succeeded? So they address both these issues, and they say, well, what if we collect a bunch of data and what if we train a vision model? So remember, we have G sub t. G sub t is what the model wants to move to. So we kind of have a goal, but the goal isn't exact. Like if I have, say in this example, say I move it right here on the edge, but the goal image itself had C in the middle. You can't have a rule-based approach. You have to have a machine learning approach to tell you, oh, well, I mean, this is close enough, so I'm going to call that a success. So instead of, so you kind of you want to train a model to detect that. And the way they do this is, remember how we do this autoregressively? Well, where each part in the autoregressive task has the image state, it has the input state, it has the goal state and the actions. What they do is they train a model that takes in this state. I guess it would be more of this state right here. Actually, it would just be the image state. It would take in the image state, and it would take in the goal state, and it would tell you, is this a success? Is the current state that I'm in, the image state, that the current environment the robot can see, is that the same as the goal state? And since you have a bunch of examples that already have that information, because you have this big training data set, you can train an image model to, like maybe a Siamese model, to detect if these two are the same, if the image state is a success state, or if it is a goal state. Yeah, and they say you can train this to do a binary classifier used to detect if the task was successful from image observations at any time step. So at any time step, they want to see, is the state we're currently in a goal state? And if it is a goal state, then we know that's a success. And if it isn't a goal state, then we know we're either working on getting to the success or it's a failure case. So that's how they detect the successes. Now, how do you know when you failed, and how do you reset? So that is this autonomous resets with policy pools. So you look at what they notice is that you kind of have overlapping tasks where you have tasks with an end state that are the same as where that end state is the same as a start state. So say I had a task that was move object B to object A, and then I had and that was one task. And then remember, our fine-tune task is move object A to location C. Then in this case, we already have our first kind of action sequence knows how to move an object from B to A, or it knows how to slide an object around on the flat surface. And then when we want to fine tune something to move it on an elevated surface, but the end state of the flat surface agent is the same. Is the end state of that is the same as the start state of the elevated surface fine tune task. So what you can do is, say we fail this task and we drop the object here. So A moves here. Then, and you realize this is a failure because this is more of a, you realize this is a failure because it's the end case of our original slide an object. Slide an object on a flat surface. But then you can use the model that knows how to slide B to A to reset the position by moving the object that was dropped here and move it towards A, because you already know how to do that really well. And then you reset your environment and you can redo this again. So you realize it's an end case, and then you switch agents. So our original goal, I can't spell, is move A to C. So our original goal is move A to C. And then we realize that so we drop object A. So then our goal becomes move A to we'll move the object to back to the starting position A. So we drop object, and then we change our goal because we realized we failed. So our goal now becomes move it back to the original state, and then our agent does that successfully because it's seen this many times. It knows how to do this very easily. There's specialized agents that know how to do this well. So we move the object to A, and then our goal resets, and we go back here. And hopefully the agent will be able to do it successfully this time. And if it doesn't, then you can restart again. And those are the two important parts to be able to generate your own data. And you can collect all these examples and put it back in the data set. And like we showed earlier, you would train the model again using that data set, and hopefully it'll become better at that data set over time. Now, the last part, and that's basically the whole thing. You're just training this transformer model autoregressively on tasks you collect a bunch of data for, and then you can have it collect its own data set by using what we showed over here, where you detect successes and you detect failure cases, and you can reset the failure cases based off other models. And the last thing to show is just the results. The model is, like I said, it's not that bad. Yeah. So the results. Let's go to that down here. So here are the results. They do it looks pretty well. Looking through the results, I don't know if these are cherry-picked examples. I don't know how much of it is cherry-picked. I doubt they cherry-picked that much because they show this here. So if we look at all these examples, so they have like they have stacking, they have pyramid building, they have inverted pyramid building, and all the tasks here, it was like this was created in simulation, and this was created in the real world, and this was also the real world. Yeah, and this is the like claw that they're using, and this is the objects that they're using, so maybe gears or something like that. Now you can see they have a pretty good success ratio for most of these. This one, they do not. I guess they can't match, or I guess they can't match objects very well using an insertion base, but it's kind of funny. But yeah, overall they do pretty well. And then there's this part right here, which is the self-improvement accuracy. So this is the case where it generates its own data, and you can see it does. On some cases, it does it does decently well. 50%, not awesome. Like half the time, it'll be successful at lifting an object, which I mean shouldn't be that difficult. But if you notice, it hasn't lifted a vegetable before, or sorry, it hasn't lifted a fruit before, and it's only lifted, say, gears. So you fine tune it to learn how to pick up its own fruit, and then it picks up fruit, and you train it to pick up fruit again, and it does so with the 54% accuracy. It also does that with vegetables. But, I mean, the results are, I mean, they're okay for the self-improvement tasks, but it's still cool to see a model be able to do this self-improvement. And you kind of have this full cycle loop. Be interesting to see what happens if you give it even more data to see if the self-improvement works even better, or if you give it a lot more time. So that would be interesting. They also have these results compared to other models, and you can see in simulation it does really well compared to the other models on a few tasks. Like I said, I don't know how cherry picked these are, but I don't know if part of it was like it's only 4 examples, and it shows to do really well on those 4 examples, but I don't know how cherry picked it is. And in this case, it does pretty well, uh, and it does really well in some of the other cases, uh, like the lifting cases and the removal cases in the real world, compared to other models. And this is a fine tuning comparison. And notice how in the fine tuning comparison, RoboCat does a lot better than the other models. Like this model over here does not do well at all. While the RoboCat model does a lot better than those. And they give a lot more examples. They also have this one example where if they have limited data marked by so they cut down the data set even more. They show that it still does well on tasks whenever you fine tune it. So they fine tune this limit. They have this smaller data set that they use to train RoboCat, and then they fine tune it on some of these tasks, and they see how well it does. And they show that with like 1,000 examples, it does really well, but it doesn't do so well at zero shot capability, like zeros in most places except for here. And the zero shot part would be I train this generalized model and then I put it on a task it's never seen before without even training it on that task. So it's pretty cool that it can do some of the tasks without a zero shot, but most of the time it requires some training or fine tuning. And with fine tuning, it seems to do decently or pretty well or decently well on most of the tasks. Inverted pyramid building, I would imagine that would be pretty difficult. I think that would be like where you would have to do something like this, and that doesn't seem like that easy of a task for it to do. But yeah, overall the results are pretty interesting. But yeah, there's a lot more results if you wanna check them out. And they also have some examples and even more training details and parameters. This is a massive paper, but that is pretty much the gist of the model. So yeah, it was a kind of quicker than usual. I don't want to spend too much time on the like very fine grained details of the model, but yeah, it was kind of a change of pace, kind of a cool paper. So yeah, that is RoboCat.